Section 5.5 talks about two kinds of special right triangles. We call these special because they appear so often. They're two of the more common types of right triangles, and so we use them a lot of times in problems, different applications, things like that. And we can always use the Pythagorean theorem to solve for side lengths of these right triangles, but we can actually find out the extended ratios, the extended proportions for their three side lengths, and then there's sort of a shortcut to solve for the different side lengths. So that's what we're doing in this section, discussing the two types of special right triangles, and then discussing the formulas or shortcuts to find the side lengths, and then doing just some practice with different ones. Okay. So the first one is called the 45-45-90 triangle, and we can get one of these by dividing a square diagonally in half. Okay, so we would know that the corners are all right angles, and then we know that squares have the same side lengths, so we would know that this bottom triangle is isosceles, and then since the three angles add up to 180 and these two base angles are the same, then we would know that those must measure 45 degrees. Alright, so that's one example of where you would see a 45-45-90 triangle. So what we want to do next is try to figure out the proportion, right, or the extended ratio to represent the three different side lengths. Okay, so let's say that the side lengths each measure 2. Okay, then let's call this third side C, and then based on the Pythagorean theorem, we would have 2 squared plus 2 squared is C squared. Okay, so we would get 2 squared plus 2 squared would be 4 plus 4, which would be 8. And then when you square root that, you get C is square root of 8, and we're just going to take the positive square root since it's a length. And then when you simplify, this becomes 2 square root 2. Okay, so C would be 2 square root 2. So that's one example. So we could have side lengths 2, 2, and 2 square root 2. Let's do another example. Let's say that those side lengths each measured 1. Now the Pythagorean theorem would be 1 squared plus 1 squared is C squared. And we would get 1 squared plus 1 squared is 2. Oops. And then when you square root, C would be the square root of 2. So that's another option. We could have 1, 1, square root 2. All right, or in general, let's say that the two side lengths measured A, then we would have A squared plus A squared. And I don't need to call it B because I already know that it's the same as the same length as the first leg. So I would get 2A squared is C squared, and then when you square root that, the A squared part can be square rooted, but not the 2. Okay, so I would get A times square root of 2. So in general, whatever your two side lengths are, A and A, your third one is going to be A times the square root of 2. Okay. So if you try to reduce all of these, like if you treat them like ratios and then reduce them, all of them are in the ratio of 1 to 1 to square root of 2, where 1 and 1 are the legs, and square root 2 represents the hypotenuse. Okay. So we've seen before if they fit into this ratio, then to solve for those different ones, then you could think of the lengths of the sides of the triangle as like a 1x, and a square root 2 times x. Okay. And we've already looked at one multiple just by multiplying everything by 2, right? Or we could do a different one. The side lengths could maybe be 5 and 5, and then this third one would be 5 square root 2. Okay, so the extended ratio for a 45, 45, 90 triangle is 1, 1, square root 2, and it has to go in that order: leg, leg, hypotenuse. Okay, so a couple different ways to solve. Here's my favorite one, I think. I think this is the easy one to remember. So I would go through and kind of draw like a circle inside the triangle and label the edges of the circle with those numbers in the ratio. Okay, like a 1, and a square root 2. Right? And then let's say you're trying to find some of the side lengths. So let's say you know that the one of the legs is 6, right? And we have to find the other two. So if you can remember, divide in, multiply out, then to move into the center of the triangle or into the circle, you divide. So you start with the 6, and then you divide by whatever number is on the edge. So divide by 1, and then multiply out. So to get this side, you would do 6 times 1, and to get this side, you would do 6 times square root 2. Right? We could try it with maybe a square root. So let's say that the one of the legs is square root 5. Okay. Then you would divide by 1, so you would get square root 5. Multiply out. Square root 5 times 1 is square root 5. And then multiply out. Square root 5 times square root 2 is square root 10. Okay. Some people like to use an equation instead. Right. So if you prefer this, you could think of this side as x and x and x square root 2. Okay. And so let's say you're told that this side measures square root of 8. Okay. Then you would just solve equations for the other side, so you could substitute square root of 8 in place of x. So this side would also be square root 8, and then this other side would be square root 8 times square root 2, which is square root 16, which is 4. Alright, so that's another way to do it. The second special right triangle is the 30, 60, 90, and this one shows up whenever you divide an equilateral triangle, okay, starting from one vertex. So let's say that this larger one is equilateral, so all of the angles would be 60 degrees. Alright, and then let's say you drop the altitude down to make a right angle. Right. Well, now we know that if you look at like the left triangle here, okay, we have one angle is 90, one is 60, and then subtracting from 180, that would tell you the third angle must be 30 degrees. Okay, so that's the special right triangle of 30, 60, 90. So let's go through, let's try to find the ratio here, all right, for those three sides. So let's call each of these sides of the larger, the original one, we'll call them each 2x. All right, and then that would mean if I look at this left triangle, this right one, then its side lengths would be 2x for the hypotenuse, and then x for this side. Okay, I can use like a triangle congruence proof to show that this side is split up into x and x. Right? And then I need to know what this third side is. So let me do Pythagorean theorem to figure it out. So we would have x squared plus, I'll call that one b. So b squared is 2x squared. And then we would get x squared plus b squared is 4x squared. Okay, so square the 2, square the x. Subtract x squared from both sides. You get b squared is 3x squared. And then square root that to get b. right? So the 3 does not square root, but the x squared does, and that becomes x square root 3. Right? So basically what we're saying is that the three side lengths for that triangle will always be the shorter leg is going to be x, that's the one across from the smallest angle, 30, and then the longer leg is going to be that times square root 3, x times square root 3, and then the hypotenuse is going to always be double the shortest leg, so that's going to be a 2x. Right? So then the ratio of these, if you divide everything by x, the extended ratio is always going to be 1 to square root 3 to 2. All right? Okay, so here's our triangle. Let's assume that this is the 30-degree angle, and here's the 60. So the one across from 30 is the smallest, and the one across from 90 is the largest. So let's try the little trick. Let's say that you know the hypotenuse is 10, and we want to find the other two. Okay, so using the divide in, multiply out method, all right, I would put a 1 on the side that's across from 30. Then this leg gets the square root 3, and this leg gets the 2. And you would divide in, multiply out. Okay, so you would do 10 divided by 2 is 5, and then multiply out, so 5 times square root 3 is 5 square root 3, and 5 times 1 is 5. Okay, so the lengths would be 5, 5 square root 3, and 10. Let's say the shortest leg measures, let's say it's 2 square root 3. We'll pick something different. Okay, so divide by 1, so that's 2 square root 3. Multiply out, so if you want to do the hypotenuse, you would do 2 square root 3 times 2, which is 4 square root 3. And then multiply out for the longer leg, so you would do 2 square root 3 times square root 3, which is 2 times square root 9, or 2 times 3, which is 6. Okay, so the lengths would be 2 square root 3, 6, and 4 square root 3. All right, how about, what if we had the longer leg measuring 8? All right, so you would divide in, and you would have 8 divided by square root 3. And we usually rationalize these, so you can either do it now or at the end after you multiply out. So I'm going to do it right now. So remember, to rationalize, you multiply by whatever the square root in the denominator is, and do that in the numerator and denominator. So this would become 8 square root 3 over square root 9, which is 3. So basically you just don't want square roots in the denominator. Alright, and then you multiply out. So times 2, which would be 16 square root 3 over 3. And then times 1, so this leg is going to be 8 square root 3 over 3. Okay, let's do another one. Let's say that the shorter leg measures square root 7. Okay, so then divide in by 1 and you get square root 7. Multiply out by 2 and you get 2 square root 7. And multiply out, square root 7 times square root 3 is square root 21. If you like the equations method, then you would label these three sides as x, 2x, and x square root 3. Right? So then let's say that you know that the longer leg measures, let's do like 15. All right, so then you would say x square root of 3 is 15, and then we're trying to find x and 2x. Okay, so I would probably divide by square root 3 next, and then rationalize, multiply by square root 3 over square root 3, and that becomes 15 root 3 over square root 9, which is 3, and that reduces to 5 square root 3. Okay, so x, or the shorter leg, is 5 square root 3, and then 2x, I would multiply that by 2 and get 10 square root 3. All right. So these two statements, all right, are, you can read these both ways as well. So there's a statement and its converse, and this is also mentioned, I guess, more formally in the textbook, but if you have a 45, 45, 90 triangle, then that automatically means the sides are in this ratio 1, 1, square root 2. And then you can also read it backwards. If you have a triangle with sides in this ratio, then that would tell you what the angles are. So let's say I had a triangle and I knew that its sides measured 15, 15, and 15 square root of 2. Okay, well then automatically, without even checking Pythagorean theorem or anything like that, I know that this is a right angle and the other two are each 45 degrees. Okay, similarly, if I have a 30, 60, 90 triangle, then I know that its sides are in this ratio 1 square root 3, 2. Or if I have those measures, so let's say I have lengths of 3, 3 square root 3, and 6, then right away I know that the angle across from 6 is a 90-degree one, the one across from 3 is a 30-degree angle, and the one across from 3 square root 3 is a 60-degree angle. Okay, so those are the two main ideas from this video, using 45, 45, 90, and 30, 60, 90 triangles to solve for the different side lengths, and then seeing that we can also go backwards and find the angles if you know the side lengths. There are a lot of different examples in the textbook of solving for the different sides, so I just chose some different ones. I didn't go through all of the examples in the book, so you may want to take a look at those if you need some extra practice. And if you understand those two concepts, then you are good on everything from section 5.5 that you need to know.